Okay, let's start by recalling just general integrals. Now, the application of this concept is really trigonometric. You're going to do a lot of sine cosine stuff. Okay, just so you have an idea. Traditionally, when you see integration by substitution method, which is what we're going to do, you'll see you're going to have a lot of things with trig. There's some examples that don't have trig, and that's fine. You don't have to have trig in it. So if I asked you just quickly, the integral of, let's say, x squared plus sine of x dx. No limitations. Okay, no limits, upper or lower. When you integrate x squared, what does that become?
X over 3. Yeah.
Good. X to the third over the new exponent, which is 3.
Now, negative cos, negative minus. Yeah, negative cos.
You guys are wondering between which and which, right? How do you remember? You go to the derivative. The derivative of cosine is negative sine, right? It is the opposite. So the integral of this one is going to be negative cosine. Now, what do I put at the end? Good. Plus c. So just to remember that, please. Remember that the idea of integration, you can separate when it's a plus sign. Now, the question becomes, well, what if it's not a plus sign? What if we don't have a plus sign there? What if we have something else? Okay, then we have to start looking at something called the substitution method. So let's start with an example.
You're talking about for C?
To integrate in general. Because I just integrated each of them separately, right? Because there was a plus sign. But we haven't dealt with anything with multiplication. We've always FOILed it out. But what if you can't FOIL it out? So let's take a look at this example. If I had the integral of x squared, and I'm going to go to a lot of examples for this. It's the easiest way to go through this. And that's the way I learned it. I'm telling you now, just the more of this you do, the more you pick up on it. It's one of those intuitive things.
Yeah.
I want the integral of, okay, the integral of x squared times the quantity 5 plus 2x cubed dx. Okay, 5 plus 2x cubed dx. So, I mean, look at this problem. There's no real way that you're going to know how to do this off the top of your head because you can't integrate separately. It doesn't work. Again, it only works when it's a plus or a minus. If there was a plus in front of here, then you could maybe do it. And you could think of this as a 1/2 power and do all that kind of stuff. Today what we're going to do is we're going to do something called substitution. Now, I called it, when I took the class, U substitution. The letter U, not U as in Y-O-U. And there's a reason. Here's how this works. Think of one of the two quantities as U. Okay, you're gonna realize over time you'll know how to do this. But I'm just gonna pick it for you now. If I call this whole thing U, not including the radical, but just that thing right there, call that U. So let's say let U equal 5 plus 2x cubed. Okay, if I let that be equal to U. Now, this is where derivatives come into play with this also. If I know that that's U, what would du dx be equal to? What would the derivative of that one be?
5x plus 2x.
Derivative.
Oh,
6x.
yes, 6x squared.
Again, what does this become when you take the derivative of 5? 0. It's the derivative of constant. The derivative of this, bring down the 3, you get a 6. This reduces to 2. So that's the derivative, right? Do we all agree at least?
Yeah.
Okay, I agree also. Now, what I want you to do is now solve for dx there. Move the dx up, move the 6x squared down below. Solve for dx here. Again, solve for dx. Think of dx as a variable. So I want you to get this by itself. Doing so, you're going to see that dx is equal to just du over 6x squared. Is that mathematically sound so far?
Yeah.
Okay. Du over 6x squared. Now, if I know that's what dx is equal to, can't I just plug it in right there? And wasn't this called u? Can't I write that as a u? Again, we said let u equal that whole thing. Sounds weird, I know, Carrie. Carrie's looking like I got 7 heads. Call that a u. Replace the dx with this right here. Just trust me on this one, okay? Call that u and replace the dx and rewrite the integral in the next line. Just try it first.
I have a question though. Because if you change the dx, doesn't mean that you're not integrating.
Yeah, just try it. So do it, Kenny. You need to keep these, thoughts and just try and actually go through the problem yourself. These are good questions, but I want you to discover and do it. So go ahead and write it and then try to continue if you can. Some of you might notice something. Think about what you could possibly do after that. Again, I'm substituting in for those two spots. So on your paper, I hope I see this now. That's what I should see. Does everybody have that written down? Well, take a look what happens, guys. You have x squareds, don't you? One's on the top, one's on the bottom. What happens to them? Don't they cancel? So now, if I look at this, I'm actually integrating radical u over 6 du. Again, cancel, cancel. Wait till the second time to get caught up because this is probably like gibberish right now. So, radical u over 6 du. Well, take a look at this problem. Now you can integrate that. There's no more product. Look back at the beginning, God bless you. We had this product here. But now, we don't have a product anymore. We've got a value, radical u. What's radical u? How do I write that? U to the 1/2. So, take out the 6, because remember, any constants that are multipliers can come out front. That was one of our rules from integrals. So put a 1/6 out front, and you're doing the integral of u to the 1/2 du. And now, as Kenny said, we're not integrating with respect to x anymore. What are we integrating with respect to? U. And this is an easy integration. How do I raise the integral of 1/2? 3/2. Good. Remember, 1/2 plus 1 is 3/2, divided by 3/2, with a 1/6 out front. What else did I put? What is it?
C.
Plus c, thank you. Again, no limits. We got to always put the c up front. Remember now, you don't have to write divided by 3/2. You can multiply by 2/3, which is the same thing. And I hope you guys do that by now. Okay, again, that 3/2 right is 2/3. So you might be saying to me now, okay, Mr. Howe, great. Now I got this u thing. But we started with x, didn't we? Well, didn't we define u in the beginning of the problem? We defined u as 5 plus 2x cubed. So just rewrite this, but instead of a u, put 5 plus 2x cubed there. So this is now, again, I'm going to write it this way. 1/6 times 2/3 times, now instead of a u, I'm still going to have a 3/2 power, plus the c at the end. Instead of the u, now I'm going to have 5 plus 2x cubed. And this, simplified, obviously, we can simplify the fractions, but this is the integral. So you didn't even touch x the entire time. You started with an x in the very beginning. We defined u as some value, defined du dx, solved for dx so we could replace it up top. We then carried out the process. How did I do this to this?
Yeah.
Because dividing by 3/2 is the same as multiplying by the reciprocal. The reciprocal of 3/2 is 2/3. This reduces, right? Reduce, reduce. This becomes a 3 and a 1. So your final answer is really this whole thing over 9. And I could really put c over 9. I could distribute the 9, but it's still a constant. Remember this whole thing we talked about with k and c? A constant is a constant. If I put c over 9, because technically I should, or over 3, I should be distributing the 6 to everything, like 1/6. But this would be over 6. It's still a number. It's just a constant. We don't know what it is, so it doesn't matter at this point. Okay? So the integral, this is what the integral turns out to be, actually, right here. Now, the question that you're going to have to figure out on your own, and this is the hardest thing to do as a calculus student, it really is to figure out what is u in the beginning of the problem. You know how I gave you guys u? I said let u equal this. Some problems in your textbook that I gave you for homework, they tell you what to use for u, to kind of step you through the process. But over time, you'll figure out there's certain times you should use it and certain times you should not.
Yeah. Putting u in, if we use u in like one of we're not supposed to exactly use it.
It won't work, and you'll see you have to go back and do it again.
Okay.
Yep. So you know what? Let's look at the same problem quickly. Same exact problem, and let's call u the beginning instead of the end there. So let's say we had, again, integral. You can write this down as like the wrong way, or just write it down as something that will not work. Okay, I've got two parts of this. I've got the radical and I've got the u part. I've got the front part. So if I said, let u equal x squared instead this time, I decided to do it that way. What is du dx now? So solving for dx, again, you're always solving for dx, so you can plug it back in. Solving for dx is du over what? 2x. Now, if you plug that back in up top, you're not going to have the same process again. Watch what happens now. I now have, again, I'm going to plug it back in up there eventually. I now have the integral of u squared, but that's u, of x squared, but that's just u. So I now have the integral of u times radical 5 plus 2x cubed times du over 2x. So if I did u substitution this way, the problem is that, look, is this going to be able to cancel now? Remember last time when we got to this step right here? When we got to this step, when we plugged in for dx, we canceled the x squared, and we're left with only u. But in this process, we're going to see that we can't just cancel stuff now. So choosing u to be equal to x squared yields this mess, really, because these don't cancel. So I can't integrate with respect to u. I can't think of x as like a constant or anything. This doesn't work here.
So does that mean really will always be, like, will you always work? You just have to pick the right.
There's always going to, if a problem is given you on the test that's an integral of products, there's a good chance u's are going to work. The only time it wouldn't work is if you have to do it on your calculator. Sometimes they'll give you functions that you can't integrate, and they want to know like the area under the curve. You've got to use your calculator to do it. There was another technique, and there is another technique called integration by parts, which was always on the AP exam until 2 years ago. They took it off. They now pushed it to the next exam, the AP BC exam. So if you'll notice in the syllabus that I put online recently, it's one of the extra topics, integration by parts. We'll learn that also, because it's a good technique, and you'll definitely use it. Okay, you'll use it in calculus too.
Does that mean you should always be the part of the
Yes,
function which
should be one to. Okay.
The most, I mean, obviously the higher degree, like if the most amount of like coefficients in it, that'd be like what you choose u to be.
Not necessarily. You got to think about, pick the u value. When you take its derivative, will its derivative cancel out with something? The 2x clearly doesn't cancel out, right? But when I choose the inside to be my derivative of the original problem, look at the derivative of this. It's going to be x squared, right? And I see the x squared. That's what gave me the correlation.
Do they have to cancel or can they simplify?
They have to. You have to get rid of all your x's for this to work.
Okay.
X is OS is disappear. It's got to be all u's. Okay? It's going to be all u's. Yes. Can you go where? Can you be very quick, Rosie? Please. We're going to do more examples. I don't want you to fall behind, and we're going to do a lot of tough examples here. Okay. Let's do. Let's look at the integral of the cotangent of 7x dx. Start by remembering to yourself, first of all, there is no derivative that gives you cotan as an answer. Okay? The only one that you get for cotan of an answer is cosecant squared, but that has to do with the derivative of cotan giving you cosecant squared, so it's not going to really help you. So, to start a problem like this, what does cotan really mean?
Cos over sine.
Cos over sine, cos over sine. Remember, tangent. What does tangent mean? Tangent is sine over cosine. So cotangent is cosine over sine. So start, whenever you have a cotan or a cosecant problem, if you don't know the answer right away, there's no integral for this, start by replacing with trig functions. Okay? So start by your standard ones. So cosine 7x over sine 7x. That's one hint I'll give you, okay? It looks like it's going to be messy at first. It does, at first. It's actually not that messy, though. Now, for this problem, here's what I want you to notice for this. Think about the fact that the derivative of sine is cosine, and derivative of cosine is actually negative sine. So when you take their derivatives, don't they become each other?
Yes, well, one's negative.
Okay, but one is negative, but they become each other, don't they?
Yes.
So if I am taking the derivative here, there's a good chance that they might cancel each other out. So, Christian, we have two options here. I could let u equal cosine 7x, or let u equal sine 7x. Which one should I do? Sine? Okay? Works for me. I'm not going to argue. So u equals sine 7x. Okay? So what's du dx? Just cos 7x. Be careful. Again, no negative there. Derivative. Solve for dx, please. So switch these two spots. You're going to get du over cos 7x equals dx. Again, how do you solve for it? Please don't actually do math. Just flip these two around. You got to pick up on that by now. Whenever you have 3, you can move the diagonals. Or 4, either one. Now, in this case, we want to replace our dx. So let's go back to our integral now. We're going to take this value, plug it in there for dx. We're going to take this value, sine of 7x, and replace it with a u. So this is going to become the integral of cos 7x over u. Where did the u come from again that I'm putting in here? The let statement right here. We let u equal this. So if u is equal to sine of 7x, we replace the sine of 7x with a u. Then I take the dx and I replace it up here. I replace the dx with du over cosine 7x. Karen? They canceled out. Again, this du over cosine 7x goes in for dx. So you no longer have a dx. Cancel. Cancel. Is that evident? Now, again, the hard part, what's the hard part? What's u? That's the hard part. Figuring out what to choose for u here. Actually integrating, the easy part. What's the integral of 1 over x? What is it? ln. Awesome job, Kerry. Remember we've been using the absolute value with that last one we looked at? Start writing it that way, just to be safe. And now, this is not x. What is this really? Sorry? U. Again, take a look. Once you see the cancellation, you're left with just 1 up here and a 1 down here. You get 1 over u du. But the derivative of ln is 1 over x. So the integral of 1 over x is ln. Let's talk about that in the next part. Let's derive it. I wanted to show you that. Try it yourself. Try it on your own because you're done already.
Wouldn't it be negative?
Try it. Try it. You'll see the correlation. You'll see what I mean in a minute. Just try it yourself for once. Here, not for once like that. I mean, just for now. The value of u, though, what was the value of u in the beginning? What did we define u as?
Sine of 7x.
Sine of 7x. Okay, so that's really the answer. Remember, the answer is not ln of u. U is something that we made up. We just invented this let statement with u. Now, one thing I want to notice, and I made a mistake, I apologize. Everything's right, but one thing. When we took the derivative before, what did we forget to do?
Plus c.
Not plus c, actually. Go back up to here and take a look at this. Edgar, pick it out. Figure out what it is. From here to here, what was the mistake that I forgot to do? When you take the derivative, what kind of a rule is it really? What is it? Chain rule. Remember, the derivative of sine is cosine, but then you got to multiply by the derivative of this. What's the derivative of that? So please go ahead and put a 7 here. So it's going to put a 7 here, which is fine. It's just going to be putting a 7 in front of everything. So you put the 7 in front of the du dx there, which puts a 7 here, which puts a 7 here, which puts this over 7, which really means a 1/7 out front. I don't want to mislead you there, and I apologize. I was getting too antsy with that. So here again, you're going to have du over 7, not just du, because these cancel, but you're left with that 7. Factor out the 7 in the front because it's a multiplier. You can just move it out front. Questions? I know it's a tough problem. I know it's not easy, but we got to make sure. We got to make sure for these kinds of problems here that we're thinking about the fact that when we take a derivative, we take the derivative correctly. Because I screwed that up with the derivative there, and we saw that clearly it's a different answer. Christian, what do you end up getting when you do it the other way? Yep. Did it work, first of all? Did stuff cancel? Okay.
I just thought that Your derivative of cos negative sign.
Derivative of cos negative sine,
So
good.
then you get it's the same thing, just with
What does your final answer come out to be? Did you get the final answer yet?
negative and then 7 parentheses.
Oh, sorry, negative 1, 7. You mean,
Yeah,
right?
sorry.
Negative 1, 7.
ln. Can you have a negative one?
In the front you can, sure. You can't have a negative inside of the argument. Outside you can.
Cos 7x.
So the negative here and the cos here, and let's try that. Let's actually graph it to show. So what Christian is saying is this. For this problem, had we chosen instead of sine of x, we chose cosine of x to be our u. See what we get for an answer. So if you want to just write down the answer, I'll go through it real quick though. So if we have integral of, again, we're doing cos 7x over sine 7x dx. You can write this if you want, or you can just watch. If I let u equal cos this time? Yeah, thank you. I don't want to do the same thing twice. Cos 7x du dx is going to be 7 negative sine 7x. Okay, derivative of cosine is just negative sine with the 7 from the chain rule. I solve for du or dx. I'm going to get du over negative 7 sine 7x equals dx. I then plug in. Now I'm taking the integral of u over sine 7x times du over negative sine 7x. Are you sure it worked, Christian? So you said it worked, remember?
Yeah.
I don't see it working here, to be honest, because why? What happens right now? Where am I at the point? They don't cancel, actually. Again, when I solve for dx, I get du over 7. But in this case, I have the same thing in both, so it does not work.
So how do you keep my that close to the top?
Ah, okay.
I've always been the same process.
If u is equal to cosine, now the u goes up top. That's the hard part there. Okay, so this would not work. This would fail to work. So you have to go back and pick the other u.
It sucks.
Right?
You do the whole.
But you know how you just answered your own question. That's what I want you to do there. Because honestly, off the top of my head, I wasn't sure. That's why I want you to check in your own. I want to tell you one thing when it's not the truth. Whenever you're unsure about something, please try to investigate on your own. That's how you learn. Let's try an example of... Okay, this is an interesting one to look at.
Yeah. That's how you get up there.
dx over cosine squared of 2x. Okay, the integral of this. Which can be thought of, obviously, as 1 over cosine squared 2x times dx. Which is what you're used to seeing, by the way. Okay, again, you're used to seeing a function and dx at the end. So if you want to rewrite it that way, start by doing that. Okay? What is 1 over cosine equal to? Secant, right? Secant in this case. So I could start by first saying, all right, let u equal cosine of, cosine of 2x or cosine squared of 2x. Go through the process. But what I do want you to keep in mind is the check. If I knew that this was really secant, if I knew that that was really secant, when do I get secant squared as a derivative? Tan. Remember, the derivative of tangent is secant squared x. So the integral of secant squared should be tangent. Remember, an integral is antiderivative. So here, the derivative of tan is secant squared, so the integral should just be tan. But the problem is I have 2x, not just x. I have 2x here.
So you just put the u with the 2x?
What do you do?
You change the 2x for a u?
Very good, Kenny. Let u equal 2x here. Because if I have secant squared of u, right, that would become secant squared of u.
Yeah.
I can integrate that,
Tangent of u.
because secant squared of u is just tangent of u, because it's a u by itself. I don't want this 2 here. So start by saying, let u equal 2x. Good notice there, Kenny. Let u equal 2x. If you see that, then you can say, all right, well, then du dx is simply, what's du dx?
2.
2. Again, the derivative of 2x is just 2.
Switch.
Switch the dx and the 2.
Du over 2.
Go back to this function right here now. Go back to this one. Put that a u and plug in for dx.
We can't it over. This one. It says we can't it over to the club. It's the same too.
It's the same with every class, Kenny.
I know, I'm just saying because I don't know, it just feels nice to do it over.
Again, if you plug in these two values, you solve for dx, you plug that in up here, you solve for u, or you set u equal, you plugged in up there, that's what you're going to get now.
1/2 in the front.
Okay? So what do you do in the front, Kenny?
1/2.
Just put a 1/2 out front. Remember, divide by 2 is the same as multiplying by 1/2. So if the whole thing is divided by 2, and there's a multiplication sign, I can factor it out, really. Put a 1/2 out in front, and now I'm doing the integral of secant squared u du, which I know is tangent, as we said a minute ago, because the derivative of tangent is secant squared. So this becomes 1/2 tangent u plus c. Okay, I really, theoretically, guys, I should put parentheses, but what did I say before about the c? What is c? It's a constant. So if I multiply it by 1/2, is it still going to be constant? Yeah, it still is. So who cares about it right now? It's a constant either way. We don't know what it is, so whether it's c or c over 2, it has no effect on us. It is. So here, I know that this is u, but what was u defined at in the beginning? So if I have a very basic function, can somebody make a correlation now? U substitution is worthwhile, but for this problem, I would not have done U substitution because I picked up on something. What might you have picked up on? What do you got? A chain rule. There's like a chain rule here going on, isn't there? The chain rule of derivatives, you take the derivative, and then you multiply by the derivative of the inside. But what are we really doing here? What are we doing? We take the integral, but then do we multiply by the derivative?
No.
We actually divide. Take a look. The derivative of the inside, what's the derivative of 2x? 2. Isn't that what we're doing here? Are we really dividing by 2? So there is actually a chain rule of integrals. Now, the problem is that a lot of people think they can just do the chain rule. A lot of the time you do need to use substitution. You do need to use it. Okay? So don't let that misconstrue you there. You do need to use U substitution. So here's what I want to do. I want you guys, somebody else to take over, write down a list of steps for this. On your own, after what we just did, who can tell me what steps would be? And somebody else write, somebody else dictate.
I can write.
Go up, yeah, go up, right?
I can write what you dictate, yeah.
Other people, not just one person, please. What are some steps? And I want you to agree on the order of the steps. Don't leave anything out. What are some steps?
That's my paper too.
Give suggestions, and then you can argue with each other. But I want you to come up with the steps on your own here.
Well,
This is how I do the stuff too, guys. Come up with your own steps. I don't just find steps. I make them up.
we'll still
What did we start?
yeah, we'll start writing the equation. Say fart. When we
You
fart.
say, what do we first do? And when we start, I said, what do we fart?
Hey, well,
What do we start with?
equation.
Yeah, first have your thing you're integrating.
Or separate, like,
Ken, I think you should talk before you just start
Yeah,
writing.
yeah,
So
yeah.
tell everybody what you're about to say first.
Wait, writing the equation first, or
Well, you have to have an equation.
fine? So what
You're
equation?
given an integral, guys. You're given an integral. Sorry.
Okay.
You're given an integral. What are your steps to find that integral?
Okay, so then,
Yeah, you don't need to write it, sorry.
well, we have to
You
define
can-
the u.
I thought,
First,
We look first. We look at it and we define what we should place as u. That's what you said before, right?
I'm trying not to say anything.
No, no, I'm
should we
looking.
separate it first, like make it easier, like how you
It gives me-
put it one over? It's not always given like that.
Yeah, it's better if he gives the equation. It's easy. What do you mean?
oh, well, you should just say like,
Think about if
that was
statements.
just that problem though.
For the first step, think about if
Yeah.
statements.
Oh, so if
Oh, so if not added or subtracted, like if it's multiplying, then you have to
or
use
dividing.
substitute.
yeah, you're right. If it's say it again.
If the function is multiplication or division, you pick one of the
Arguments.
arguments.
Yeah.
One of the arguments.
B, B.
Says a function.
Yeah.
FN for function. No, just FN. Like, abbreviation to the word function is just FN.
Okay. Yeah, I was just saying f of n. Yeah, that's for some reason because it is really function anyway. So if the function is
Multiplying or dividing.
then
Choose one of your arguments to be known as u.
To B. How about the word B?
yeah.
I put you in parentheses.
Yeah. Huh?
Yeah.
Kenny, you goes in quotes, not parentheses, quotes. There you go.
Choose one argument to be.
Okay,
B.
so that's a really good step. Now, before you put number 1 next to it,
Oh, so I'm sorry.
what Karen did say a minute ago should be considered. You don't have to write it down, but there are times where you might want to change the function before you pick u. Like, remember
Yeah,
how we had cotan, where we made it cosine over sine? So
So if-
before that, I might write, like, if possible,
simplify.
rewrite, or I would put, you're not simplifying, Kenny, you're just rewriting.
See if I can do this like Mr. How do you move it down?
Just drag it straight down.
From
So
Miss-
if possible, Karen, you word it, because this was your choice.
Yeah,
If possible, what?
It's like separating, but at the same time you're
rewrite it.
yeah, making it easier.
So rewrite it so it looks what? Integratable, clearer, simpler, different. So if possible,
Whatever.
rewrite in a
You're in a simpler form.
simpler form or more usable form. Because you're not simplifying, so I don't want you to
Yeah.
think of word simple. Okay? In a more usable form or more versatile form, in a word.
Developers. I'll just put usable.
Yeah. Made a word.
Forms.
And yeah, if you want to put like a little star next to it, just to show that you don't have to do that, it's not necessary, but it might help you in the problem. Okay, call that a star and then start with 1 after that maybe. Alright, second step.
After we did that.
The inequality.
We did
Derive.
derive.
Yeah, we
No,
did.
no.
Wait, we did we derived it. We did the derivative of what we picked to be u.
What is that
So-
called when you take the derivative of something? What's the fancy word I use?
Differentiate.
Differentiate.
So, okay, so
Or just put take the derivative of, either one.
okay.
Or you can start with different.
Differentiate the value of u.
Differentiate.
No, it's
the
two. Is that
value.
too?
Talk to your classmates.
Differentiate the value of u, or is that too ambiguous in a way? Because then it's like.
U doesn't have a value. I just gotta start by saying that. U's not a value.
Yeah, but
You're
Take the
differentiating
derivative of the value.
that you chose for you. Like you're
Yeah.
differentiating
The
the,
argument that you
yeah,
chose.
the argument that was chosen for you.
Or-
by arguments, the whole thing.
Yeah.
Okay, so yeah.
Yeah.
What are you differentiating with respect to for this one?
du or
Du,
dx.
yes.
It's du dx. So differentiate with respect to x. Put that after that, please.
Differentiate.
And in parentheses, put with respect to x, parentheses. And just use WRT with respect to. You'll see that a lot. WRT. You can put periods.
That means with? Oh, with respect to
Yeah, I know. It's one of those weird with respect to
x. Wait, so differentiates. What'd you say, Carrie? Was it you that said it? The argument.
With respect
Differentiate.
To,
With respect to x.
Ar-
The
argument.
argument.
For you, chosen to
differentiate
give
with
you.
respect to X. Yeah.
So you're really just differentiating the argument, but put with respect to x in parentheses. There.
Okay, should I just put chosen to be u? So that go now?
That's what you need.
Okay.
You said before, look, the argument is you, right? So
Yeah.
by default, if you're saying differentiate the argument, when you're saying you.
Okay.
Changeable there,
True.
right?
True.
Transitive property?
Whatever you said.
Right. Okay. Then after that, we made it. What do you call it? We switched the.
dx.
Yeah, we made dx
we
equal.
solved for dx.
Yeah. We solved for dx, and after that we.
Substituted back to the
No, we substituted dx and the u.
That's correct. Oh,
Yeah, we placed the u in for the. We put in the original argument we changed it for u.
Use that 'cause easier to remember to put it back
Plugging in what we solve for dx.
and solve. Or what is you?
I would just say plugging in and then make it like a
Plugging what is
subset in that. Plug in and then like dot dot, and because you're plugging in two things, aren't you?
Yeah.
So now the next line make a little indent a little further.
By what do you mean indent? Like.
No, like you know on the AP test they have like.
Yeah.
Oh, okay. That's what I was gonna do. Is
You're
just
gonna do both of
yeah,
those.
yeah. And so it was like for dx. What?
Plug in dx
Yeah, for dx.
in the overall, or no, in the interval.
You haven't integrated yet, so you're just plugging in dx into.
Okay, and then
Into
what,
the interval.
what is u?
And then what else did you do?
Plug in u for the argument.
Good. Plugged in u for the argument. Okay, the defined argument, really, that's what you're looking at. Remember, you defined it as you. You as in you guys. Good. Yeah, around the u, whenever you do like a variable like that, either italics for typing, but when you can't, obviously.
Yeah, just put you, just so that people don't get mistaken with it. For slang. Wait, up.
No, she said go up.
Oh,
Yeah,
up.
just slide up. See that? Okay, once you did that, guys, what was next?
Yeah,
Good,
we cancel. We
good.
see if it cancels.
See if it cancels.
Yeah, 'cause if it
Absolutely.
doesn't, and if it doesn't cancel, we go back and
This
change.
is where you have a loop, right? You know what a loop is? If it cancels, go on. If not, you loop back to the beginning and you start over.
Yeah. So would there be like an A and B or just make it an if statement?
I would just
Like-
say an if statement. So for step
Yeah.
5,
Hey,
You done? Okay.
yeah, you guys come up with these wordings here.
So
Jocelyn,
Wait.
do this one here. What are we going to do here? So once we plug in our for dx, we plug in for u. Okay, we look for cancellations. How can I write an if statement? Because I have two conditions. Either it works or it doesn't. So I want you to make a statement that says both of those. So you're going to have two paths to choose from. Write those out. Tell me what they should look like. Want help for half of it? Okay. If
okay. So I'm writing what you.
If all x's do not cancel, if all, and quotes, x's do not cancel,
you choose the wrong.
then start over and choose a new u.
Isn't it?
That's not giving you a whole.
Don't put cancel, just say
Do
start
not-
over, because you're not canceling anything.
Do not
Cancel,
cross. Wait, what did you say?
then start over.
Do
There's
not.
no do not, just here's the do not. If all x's, oh, I'm sorry.
You
no.
need it.
You said
Yeah. What do you like?
I apologize, Kenny. I'm so sorry. You're absolutely right. Well, do not cancel, then start over.
Yeah.
I think you're saying cancel the problem. Sorry. Then I saw cancel. I thought
Then
I
start
told you the
over.
problem.
Start over and choose another U.
Start over with a new u. Good. And start over with a new u. Now, Jocelyn, tell me the other possible scenario now.
Cancel.
And what do we do next?
The interval of
Good. If they do cancel, then just integrate. But if,
all the same one.
But if it does cancel, or should I just
Sure,
put?
that's fine,
wait,
that's
or-
fine, Kenny.
I was thinking of like, well, making it A B, but I was like,
No, because
but it does cancel.
the word you're thinking of is like
Integrate
else. For all else, you're going to do this. And in coding, you can call else if. So if anything else happens, or if they do cancel, but if it does cancel, then just integrate. For those in physics, quick question for you. Have I ever showed you guys the clip from How I Met Your Mother? Oh no, Big Bang Theory, where he does, I've showed you a lot of those, but I showed you the one where he has this like chart, with a bunch of if statements and programming
No.
language, if like how to make a best friend or something like that.
No.
It's hysterical. I'll show you, okay? Because it's all about if statements like this, and he gets stuck in the infinite loop. He keeps trying stuff and nothing else works. He keeps doing it over and over. Okay, that's step
Okay.
5. Step 6, there is one more step. Because you integrate, right? And your answer is all you, though, in the answer.
Oh wait, we plug in back. We plug the argument back in for you.
Very good.
MSC.
Sure, but the C goes with part.
Yeah, because yeah.
When you integrate, you have no constants. The C is automatically there. You want to put don't forget C. At step 5, yeah, in the parentheses step 5, don't forget C.
Forget C. Like C doesn't matter. Okay. Well, wow. Okay.
No pun intended.
Add C. You add it to C. Like,
Not like
add
add
C. Like, because you're adding C and then you're adding C.
Don't forget to add C. Wait, who are you talking to?
Oh,
I'm so
add is
confused.
in the English word and then add is in the mathematical word. I got you. That was too far for me there. Don't forget to add C.
Or like yours.
Just don't forget C.
Yeah, I was like,
I don't get it.
Yeah. Add is in added to the line or add is in the plus. So plug in argument.
Good.
Okay? So again, guys, I don't just, copy steps from somewhere. This is all you got to do. Go through the process, see what you did a few times, and now you can use this process every time you go through your steps. And you know what, though? I don't need to memorize these because once you do enough of them, you actually understand it. And you get yourself, oh, well, I got to do this because of this. This is the reason why. Here's why I do this. Oh, it didn't work. Go back to the loop. Start over. Now let's try another one. You're going to have problems like this in the exam where you might choose U and it doesn't work. Try another U right away, please. Or look for a mistake in maybe your work also.
will this always work for?
For the examples they give on these, they do. There are some functions that cannot be integrated. And the only way you can integrate them is what's called numerical techniques. And they're very, very, very complicated. We're talking like graduate level calculus.
Okay.
You don't even do that in undergraduate. Okay? Some of them you can numerically integrate on a calculator, but you need to have the limits. Remember that?
Mm-hmm.
Like going from 2 to 7. But if you're integrating with no limits, some of those methods are very, very, very complex. We're talking like pages of solutions.
But does this like integrate pretty much like everything that we've learned before, which is integratable?
Product rule, quotient
Yeah.
rule, that stuff, it all lumps into this really.
Yeah, okay.
Into one method. Okay?
And this will always be the same way? Or were there...
Same steps and stuff.
Yeah.
Yeah, there's not going to be any real difference here.
Right.
Again, because they took that off the topic off. There was another way to do it, which is a little more complicated because it involves harder problems. But it's not on there, so I'm not going to go into it before the exam. It would just confuse you right now. Not confuse you, but it's more information that's not needed this minute.
Yeah.
We will get to it though.
Right?
Still have 10 minutes.
Do you really?
Trying to think of what I want to do next though. Hold on.
Practice.
And let's do one more, we should let us do ourselves, then we can see the right answer after school. We are trying to go over the next. That's why I'm making you do your own problem.
All right, this one's a tough one. It's difficult to see this right away. Okay, it's very difficult to see this. Now, before I go into this next example, please tell me, who remembers Pythagorean triples? What's an example of a Pythagorean triple? 3, 4, 5,
5, 12, 13.
5, 12, 13,
Here's what that we remember those.
8, 15, 17. Okay. Yeah, 6, 8, 10. That's another one, because anything times 2 works also. So you double any of those. Instead of 5, 12, 13, you do 10, 22, no, 10, 24, 26. Anyway, remember Pythagorean triples. Now, here's the hard part. Who remembers trigonometric identities that are actually come from Pythagorean triples?
Cosine plus cosine equals 1.
Good, okay. So remember the idea, right?
Yeah.
We're going to use one of those here. That's why I'm trying to give you a little preview.
Alright? I don't need that. I just don't want into that. I want to the belt. Okay.
Now, earlier we did an example with cotan, right? And we wrote it as cosine over sine, and we used that.
Yeah.
The problem now is that it would be cosine squared over sine squared, which when you take the derivative of cosine squared, it's going to be a lot messier. Okay? Because you have a chain rule in there, and stuff isn't going to cancel. So I'll tell you now it won't work. And I knew I wouldn't just tell you that, but I'm going to tell you now for the sake of time. So what I want you to try to do is, what is your Pythagorean identity that uses cotangent? That uses cotangent.
Correct.
The one with cosecant.
Yeah, it's like, yeah, cosine
Nice smile.
Okay.
Secant plus 1.
No.
Cotan is equal to just cosecant squared minus 1.
Oh, minus 1. Oh, wow. Wow.
Okay, the reason I know this is because
Sorry.
the The general one always comes from sine and cosine. Do you want me to show you the quick derivation? You never have to memorize these, by the way, ever. Here's why. First, side note, we'll come back to this problem. I got to show you this because it's a real important part. If you have a unit circle, remember, x squared plus y squared equals r squared. Okay, this is x, this is y, this is the radius, but x is really cosine and y is really sine. So from this I know, yes, x squared plus y squared equals r squared. Well, when the radius is 1 in the unit circle, this x becomes just cosine squared plus sine squared. Ignore the x, it's just whatever the argument is, call it u if you'd like to, it doesn't matter. So we don't confuse the x there. Okay, equals 1 squared, that's where the original one comes from, that everybody seems to know. You can get all the other ones from this, every one of them.
Yeah.
Who remembers? You learned it last year in pre-calc.
1 minus cos equals sine.
Okay, easier, before that, what do? There's an easier way to do
You
this.
just change the cos.
You move it, right?
You could move it, but even easier than that.
You just change the values of cos squared and sine squared. Well, cos and sine.
Okay, you're all forgetting this one, and maybe you didn't learn it this way, so if you didn't, it's understandable. Divide everything by cosine squared. Everything by cosine squared. What does this become?
Nothing.
What's sine over cosine?
Tan.
So that's tan squared u. What's 1 over cosine now?
Secant.
Wow.
See how easy that one comes about? Now take everything, instead of dividing by cosine, divide everything by sine squared. Divide this by sine squared. What's cosine over sine?
Cotan.
Cotan. Divide this by sine now. You get cotan squared u. Divide this by sine. Divide this by sine.
Cosine.
Cosecant. 1 over sine is that. So take a look at what I wrote in the last one. I don't know this out, but I didn't write it that way. I did this in my head real quick. I said, let me just divide by that, and then I moved it over. So I moved this one over here. So when I move this over, I get the negative 1. So that's why I said cotan is equal to cosecant minus 1. If you go back, you're going to see cotan equals cosecant minus 1. That comes from this law here, just moving the 1 over. Why did I define it as cotan for you guys? Because take a look, that's what's there. Cotan is there. Okay? Are we kind of clear on that? I know it's tough.
Does that make it easier?
Oh, it's an option. It's an option.
Yeah.
I'm trying to give you the right option, so I'm giving you a little bit of a hint. That's all. Okay? So here, let's go ahead and rewrite this. Cosecant squared x minus 1, and now
3x.
be careful. Yes, thank you, Kenny. It's 3x, whatever the argument is, dx.
And then we should make the 3x into u. Before.
Why is 3x equal to u, Kenny?
Because it's what I felt that works.
Wait, where are you?
Why did
Because-
I choose
because-
cosecant
because-
squared to put in? Okay, x alone, sure,
It's the dx.
but there's more than that.
You don't want chain rule?
Because you can't integrate.
You can't integrate cotan, first of all. So you start by either saying make it sine, cosine over sine, or use a trig identity. But you can integrate this. This is integrable. You can integrate it. That's why u is 3x, because this can be integrated. What comes out to be cosecant squared when you take its derivative?
No.
Ooh, we gotta go back and look at those guys. The derivative of cotan is negative cosecant squared. That's where this is gonna come from. So if I integrate this, I'm just gonna get back to cotan, but not cotan squared, cotan. Again, if you wanna write a little note, the derivative of cotangent x with respect to x is simply negative cosecant squared x. That's what the derivative is. That's why I'm using this now. Because now that I see I have a cosecant squared, if I want to integrate it, it goes back to cotan. Goes back to cotan. It'll be negative, fine, no problem, but it goes back to cotan.
So it cancel out.
So I'm going to say u is equal to 3x. What is the integral of the 1 going to be, guys?
1x. Negative
1x.
Negative
1x. And the negative, good. Remember, you can integrate separately now because there's a minus sign. The minus sign allows you to do that. So here, if I were to look at this one, I say,
So does that mean that we just leave it alone until the end? The negative 1? Because wouldn't that change?
yes, leave it alone the whole
because,
time.
Because x changes anyway to u.
But it doesn't matter because there's no x on it, so don't worry about it.
Yeah, but when you have to add it on if you integrate though.
After that, isn't
No, because do you But I mean.
Oh yes, Ken, I got you. You're going to end up having a 1/3 out here, and this is going to be a 3x, which will get back to x. They'll cancel. I'll show you. Okay? There's a reason for it. What Kenny's saying is this, guys. If we just separate it and do them separately, as opposed to just leaving it in here now, doing u's, plugging the x back in, are we going to get the same? We will. That's the cool part. But you could separate this at this point, and just do the integral with x here, and use the u's over here only.
Okay.
You hear what he's saying again? When you add and subtract integrals, you can really separate them. So I could just separate this at this point. I could write this, and you don't have to do this right now, but I could put a dx in right here, and just do another integral of that right there. And integrate this with x, and then try and integrate this with u. Okay? Or just subtract the integral, either way. Right? Subtract the integral or the -1. They're both the same. So either way, you're going to have a minus sign. Now, if let u equal 3x, take that derivative now. What does du dx become? 3. And notice then, swapping the dx and the 3,
Oh, I see.
du over 3 is just dx now. So this is going to become du over 3.
Yeah.
Well, that 1/3 is going to come on the front. Eventually, we're going to get a 3x there. They're going to cancel. That's why it's going to come in.
Yeah.
So now plug in, please. Now, this is going to become cosecant squared of u because of this 3x, and this u. That u goes in there. The dx gets replaced with this. So I still have -1 times du over 3. Now, please, 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 take the 3 out front. Take the 3 out front. Because this third here is really like this right now. And I know you don't see it this way, but this is what's really going on. Okay, you really need to have that parentheses there to show that the 1/3 is multiplying the entire integrand.
It really is.
Okay, remember, this is the integrand. It's multiplying the whole thing.
Surrounded by the u.
But isn't the
And what do you think that is?
Same idea, but this is what you need the parentheses there to show this. Because the next line I want you to write like this. You know why, Kenny? Because later it's not going to cancel out that 3 that we're talking about.
Yeah.
That same 3 that you were asking about only works if you do this the right way. If you do it the wrong way, you're going to be left with a 3x up there. Integral of cosecant squared u, we said, is cotan. So this just becomes cotan u. Integral of 1 is just going to be u. And this is going to be a 1/3 plus c. Remember, I don't care about the 1/3 being multiplied by the c.
plug back in for you?
But now the last step is to plug back in for u. What was u defined as?
Oh.
Where did the other u come from?
-1.
The integral of cosecant squared is cotan. Well, what about the integral of 1? The integral of 1 is just u.
Wow.
Right? The integral of a constant is just applying another variable to it. So the integral of like 5 would be 5u. 10 would be 10u, because we're integrating with respect to u. But now you see the 1/3, and you see the 3x there? If I actually distribute this in the next line, which I should, you'll see that you end up getting 1/3 cotan 3x minus x plus c. Again, distribute the 1/3 to both. And this is Kenny's question that he asked, actually. He said, and I'll let you write for another second. Give me another, like, 30 seconds of your time to explain this, because that's a really good question. This answer here only has x by itself. But we saw the 3x. Where does that come from? It comes from the fact that earlier, remember I said you could have separated this? If you separated this, the integral here would have been by itself. The integral of 1 is just x, isn't it?
Yeah.
That's where this minus x actually comes from, if you had separated it. Okay, after school today, we're going to continue this. We're just going to do more problems. This is one of those concepts that it's all about practice. As you do more and more, you pick up on trends and tricks. Ask Edgar. He already watched a bunch of lectures on this on Khan Academy, and he said the same thing. Trig identities, knowing what to make you is the hardest part. Okay, so please, 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 make sure you're practicing with this stuff.
Put in 0 plus these?
You already